Hey, grade 12. So today we're going to look at reaction mechanisms. And mechanisms are just the pathways by which a reaction happens. It's almost like the steps or the order in which a reaction happens. So if you look at the picture there, there's a few different options for getting up or down the stairs. One is the slide, one is the stairs, another one could be the handrail if you really wanted to. These are just different pathways. So all reactions will have a specific pathway by which they happen, and that's what a reaction mechanism is. Most reactions don't just happen all in one step. They actually require more than one step for them to happen. So in order for a reaction to occur, the reaction particles have to collide. But if the particles don't collide, you don't get a reaction. So if you think about the reaction that we've been looking at, this is just in reverse, but this reaction, according to collision theory, for it to happen all at once, you would actually have to have three things colliding. You'd need two NO molecules and one O2 molecule all to hit each other at the exact same time in the right proportion and the right amount of energy in the right place. So that's not very likely. It's not a very successful way for things to happen. Three-particle collisions are very rare. Think of like if you're playing pool and you want to make a two-ball combo shot, well, that's a lot more difficult than just a straight shot into the pocket. There's lots of things that happen in life that occur in series of steps. Everything from arranging a date, building a car, house, starting a car. Like if you think about all the steps it takes just to start a car, you have to open the door, you have to get in the car, you have to close the door, you have to put on your seatbelt, put your foot on the brake, you have to put the key in the ignition, turn the key, right, and release the key. There's a lot of little steps that happen there. It just doesn't magically happen all at once. Sometimes there could be a catalyst where you maybe have a remote starter that just starts the car all at one step or gives you a different pathway. But at the end of the day, reactions will happen mostly in a series of steps like that. There are simple reactions. We can also call them elementary reactions. And these are reactions that do happen in one step. That's what makes them simple. But more complex reactions don't. They take more than one step. So for example, the reaction that I was showing you, it's been determined that it takes a couple of steps for it to actually happen. Instead of having three things all collide at once, this way, if you do it in this process, it's a little easier and more likely to happen. So instead of having two NOs and an O2 colliding, we just need two NOs to bump into each other. And when they do, they'll form some compound, this N2O2 compound. We call that an intermediate because that N2O2 is in the middle somewhere, and then it goes and hits and bumps into an oxygen, which is more likely for a two-particle collision. And that will complete the reaction, making the NO2. And so now you get our overall reaction. Like if you go through and look at this, these are the steps, but the net reaction, well, you made this NO2 and then you used it right away. So what you're left with is two NOs and an O2 making two NO2s. There's our overall reaction. The NO2 is made, then it gets used, so it's really not appearing anywhere. It's just giving the reaction an easier path to happen. So we call those guys intermediates. And when we add those steps together, you get the net reaction, which is kind of what I just did. Now, you'll see catalysts as well. And remember that catalysts help reactions to go. They lower activation energy. They make slower steps faster. And the beauty of catalysts, and sometimes the bad thing of catalysts, is that you get them back at the end. So catalyst intermediates are almost like the opposites. Intermediates, they get made somewhere in one step, and then they get used in a subsequent step. Catalysts are used in one step, and then they're produced in a subsequent step. So you get them back. That's the difference between the two. So here's a reaction, different reactions. So here's the two steps. Now I've already got these crossed out, but what you should see here is you have your two steps. If I add them up, you can cross out things that appear on opposite sides. So the NO2 is used here. I'll put that in, used. And then it's made here. And this one is made, and then it's used in the next step. So if we cross those out, because one's used and then made, and one's made then used, it's not really changing, so we can get rid of those things. Your net reaction is the overall reaction. But we can talk about which things are the catalysts and the intermediates in this reaction. So the catalyst will be what gets used, and then you get it back later. So it doesn't have to be the very next step, but it's somewhere down the line you get it back. So NO2 would be considered a catalyst here. An intermediate is something that happens in the middle or gets made and used in the middle of this process. So in step 1, NO3 is made, and then a later step it gets used up, so it's gone. So NO3 would be my intermediate in this reaction. Now, anytime you have a series of steps, you always will have a rate determining step. Anytime you have like an assembly line or some sort of process, you're always going to have a step that's your slowest step, and you can only ever go as fast as your slowest step. Not every step is going to have the same speed. I often use making hamburgers at McDonald's as an analogy. There's lots of different steps that go into making a hamburger, but there's only one step that's the slowest, and that's cooking the patties. So if we're talking about putting ketchup, mustard, pickles, onions, and all those things, and cheese on the bun and toasting the bun, the longest thing in the whole process is actually cooking the meat. So if McDonald's wants to make hamburgers faster, that's where they're going to focus their attention. Our production of hamburgers is only as fast as the meat can be cooked. The slowest step in that reaction, so the cooking the patties on the grill, would be what's called our rate determining step. It determines the speed at which stuff can be made. In our example above, the CO molecules would have to have waited for the slower step, the intermediate NO3 molecules to be produced before there can be a collision. So you have to you're always waiting on that slower step to pick up so you can actually get collisions from it. So since our rate determining step affects that rate of the entire reaction, if we ever want to make a reaction rate change, we have to change that step. If we change any of the other steps, it's not going to affect the rate whatsoever because they're not the rate determining step. So here's an example of a mechanism. I just threw some random letters in there. We're going to talk about their rates in terms of slow, medium, fast. The speeds are not really important, just understanding that your slowest step is slow and your fastest step is the fast one, and the medium speed is whatever. They're just relatively speaking. So if we're going to go through and find our net reaction, the first thing we're going to do is cancel out anything that appears on both sides. So I look on my screen here and I see that X is made, then X is used. So I can cancel that out. Y is made and then used. So I can cancel that out. Now if I look, I don't see anything else that appears on opposite sides. So what I'm left with, if I sum this all up, I've got P, P, Q, S. Now instead of going P plus Q plus S, that's kind of a waste of time because if I have P and P, I can just sort form that down to 2 P's. And then on the other side, I have T and R. So T plus R. Well, that's kind of ridiculous. Why would we do that? Let's simplify this reaction as much as we can so you can get 2 T's and R. So there's our net reaction. Now, if you write your net reaction and you see that you've written the same element on both sides or same compound on both sides, that tells us that you missed canceling something out. Right now, there's nothing else to cancel, so I'm good. The intermediates would be X and Y. And why is that? Because they are made and then used. In this reaction, there's no catalyst because there's nothing that gets used in one step and made in another step down the road. The rate determining step would have to be just simply your slowest step. So it's step 1. So now, if we increase the amount of P in this reaction, that doesn't sound very good, but if you increase the amount of the letter P in this reaction, in this mechanism, you're going to cause more collisions in certain steps. Adding it to this mechanism is not going to have an effect on the third step because P doesn't appear in there. But if you add it to these 2 steps, it's going to cause more collisions between X and P and Q and P. So you're speeding up your 2 steps, the first 2 steps. Now, in saying that, you're speeding up the fastest step, which is really not going to have any impact on the overall reaction because at the end of the day, it's already going fast. But you're speeding up your slowest step. And since you sped up the slowest step, the rate of the reaction would increase. Now, if we decrease the amount of Q, well, if we remove Q, then let's talk about collisions. You're going to have less collisions between P and Q. So you're going to slow down that first step. And since you're slowing down the slowest step, it's going to slow down the whole thing. So the rate of the overall reaction would decrease. Now, if we increase the concentration of S, now if I add more S into this reaction, you're going to increase collisions between Y and S. So you're speeding up your medium step, which, yeah, that's great. You sped up one of your steps, but you're still going to be waiting on your slowest step. So that is going to have no effect on the overall rate. And your overall rate for this reaction, it can only be slow. You can only ever go as fast as your slowest step for any reaction. So that's it for reaction mechanisms. You can give the reaction mechanisms worksheet a try and find your catalysts, your intermediates, and your net reactions and your overall rates.